In this video, we're going to talk a little bit about strings. Now, strings you might not find very interesting, but they really do open us up to a much broader range of data structures in Haskell that we can get a good grasp on just by understanding how strings work, which is quite good for us. So why is a string interesting? Well, a string is interesting because it really is a list of characters in Haskell at the very least. It's a list of characters stuck together. Now you can see here I've got a little bit of syntax that you might not be familiar with. This is saying a list of characters. So when you see the square brackets around a type in Haskell, it means a list of that type. So you could have a list of ints, you can have a list of booleans, you can even have a list of strings, you can have lists of lists of lists. You can just put lists around most things. Another thing that's interesting is this is the structure of an actual list. So the computer sees it as something like this. When we get presented with a list in Haskell or Java, it's using syntactic sugar, which is a term we use in computer science, to refer to when the computer is presenting us with a picture that is easier for us to understand. So if we created a list in Haskell, we would get presented with an image of the list, which is not what the computer understands it as, but it's there to aid our understanding. In the same way, a string is actually a list of characters, but we see it as a bunch of characters in quotation marks so that we can understand it as a string better. But anyway, so Haskell sees a list as a bunch of things stuck together like this. So a string would be a list of characters where each character is just stuck onto the next until it's stuck onto the empty list. So this little operator in here, it's two dots, it's a colon. This is the cons operator, and it allows us to stick an element onto a list of the same type. So you could stick an integer onto a list of integers with it, you could stick a character onto a string with it, you could do whatever you want as long as you're sticking something of the type onto a list of the same type. And then the other thing that's very important to understand is this, the empty list. So this is the constructor that allows us to actually build lists. This is the final thing that is always at the bottom of a list. It's the final element. It's the constructor that tells us it's a list that we're dealing with. So if you're recursing on a list, the empty list is generally the last thing that you will check. So let's do a simple example. Let's have a look at how we would write a length function that calculates the length of a string. So let's call it length1. I think there might be already a length function defined in GHC, so I'm just going to rename mine just to avoid any conflicts. We're going to figure out the length of a string, so it should be of type string. And if we're figuring out the length, we should be returning an integer because that's how we measure length. So let's start with our base case. Now, as I mentioned, the last thing in a list is always the empty list, this constructor type here. So in the base case, I should check that I'm at the empty list. In the same way when I'm doing the factorial, I want to stop at 0 or 1. That's my base case there. My base case when I'm dealing with a string or a list is always going to be the empty list. So I just pattern match off of that. And if I'm at the end of the list, or I just have an empty list, then I should return length 0. If there's nothing in the string, then it's empty. If there's nothing in the list, then it's empty. So we return 0. The interesting case, or the other interesting case, is what do we do when the list is not empty? Well, if we look at this and we see this data structure, then what we can infer is when we're not in this case, which is when we just have this bit here, then the list can be characterized as something consed on to something else. If we only have a one element list, then it would look like this with char n consed on to the empty list. So it would be something consed on to something else. Even if we're at the very start of the list, it's char1, or the start of the string, consed on to everything else in the list. So this is where pattern matching will make our lives very easy, because the way we can represent a string in our function definition is x cons, let's make that lowercase, cons x's. So what that's saying is, Haskell, I want you to look for something of the shape, something consed on to something else. The empty case is already considered above, we don't need to worry about that anymore. Now we're just looking for something stuck onto something else. Now this is quite important in Haskell. It is very important that you get to grips with this basic representation of a list like this, because we will be using this a lot. I'm really motivating stuff that we're going to be looking at next week, but I want you to get this in your head early on so that we can have a running start when we look at lists next week. Okay, so this is the case where the list is not empty. So what should I do? Well, I should count that first element x. I don't know what x's is, but I'm going to leave that up to recursion. So what I should do is I'll do 1 plus. That's me counting one case of the list not being empty. So I want to count every case until it becomes empty. Then I'll add it on to length x's. So I've taken the first element out of the list, counted it, and then I throw it away and I recurse over the rest of the list. So this is where recursion is quite nice, because all of the logic I really need is here. The recursive call is just saying use all that logic again so that I don't have to think about it again. So let's save that and let's reload. Compiles, we're happy. So let's say length 1 and let's just mash the keyboard, get a nice long list, and then we'll hit enter, and it counts the length for us. Now of course if you wanted to you could give it the empty list, which for a string, remember we're working with strings at the moment, looks like that. We get 0 out, and of course if we just add one element into there we get 1 out. So this is a very simple introduction to lists. Strings are a list, that's something to keep in your mind. And the main thing I would like you to take away from this is one of the benefits of pattern matching. You don't have to specify what x is, you don't need to specify what x's is, you can just tell Haskell, look for something of this shape, and Haskell will deal with that for you. This is one of the reasons why it's quite nice to work with a declarative language. If you think about how you would do this in Java, if you weren't given like the length function, you would have to set up a for loop, and you would be like, have to be like for I up to whatever, while the list isn't empty, you would have to do car at position I, and then you would count, and you would have like I equals I plus 1 and count, and blah 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 blah. It would be complicated. Here is very simple because pattern matching allows us to abstract away all of the nitty-gritty of actually dealing with variables and dealing with elements of the list concretely. So so this is the main takeaway here. If you remember this when we tackle lists next week, it will make your life a lot easier. But that's everything I wanted to cover today. I hope you found this useful. If you have any questions, please do let me know. Thanks.